Welcome to lecture 2 of module 5. In this module, we have been discussing on natural or free convection heat transfer. And in the last lecture, we have discussed the basic concept, fundamental concepts and some theoretical analysis related to this natural convection, and we have seen that how to develop the equations to find out the expression for convective heat transfer coefficient. Now, as we understand that natural convection is not the theory of the natural convection phenomena is not thoroughly understood, and there are different type of situations, different type of geometries based on which that natural convection phenomena that varies, because as we understand that natural convection phenomena will vary depending upon the geometry, like whether it is a horizontal condition, vertical condition, then inclined condition. So, this is the condition how it is there, and then we have whether it is a flat plate, whether we have a cylinder, whether we have sphere. So, all these things are there for different type of geometries, different type of shape of the hot object, and then depending upon the fluid type. Okay. The theoretical understanding, theoretical derivations will go on changing. So, therefore, many a times we had to rely on the correlations, and as we have discussed several correlations for forced convection heat transfer, in this lecture we would like to discuss on empirical correlations which are available for different kind of geometries as we have discussed and different kind of situations. So, various geometry and flow situations will be discussed, and so for that what we are going to do in this lecture, we are going to discuss on empirical relations for free convection heat transfer. Okay. So, that is what we are going to discuss now. If we have seen in the last lecture also we have said, and this is there is a table. In this table, if we see that in this table there are different kind of geometries being discussed, like vertical planes and cylinders, horizontal cylinders, then upper surface of hot plate, lower surface of cold plate, then lower surface of hot plate, upper surface of cold plate, and like that, so on, irregular solids, then vertical cylinder and their height, diameter conditions, and all these things are there. And for all those cases, there is a relationship that will exist, that is we will discuss now, that we can understand that here there is a constant term C is there, and there is a power term M is there, and this RA is called a Rayleigh number. RAF is that Rayleigh number which is found out at freeze at temperature at the film temperature conditions. Okay. Now, the very common expression that is being used for such situation, whatever this is given, is that Nusselt number which is based on film temperature, average Nusselt number. This is C into Grashof F and Prandtl F whole to the power m. So, we can understand this F indicates, already we have several times discussed, that F indicates this film temperature condition, and all the properties to be evaluated at that temperature. And we have seen that C and M already in the just previous table. We have seen that there are different values of C and M are possible for different kind of conditions. Okay. Now, so if somebody has to just simply go for doing some calculations for the finding out the values of heat transfer coefficient, because what we are interested on is to find out the values of heat transfer coefficient, and from there we can find out the rate of heat transfer. If somebody is interested to go for that, then what he can find out is the Nusselt number expression, and that which is suitable for that. He can find out from the table, he can refer to the table and find out what is the suitable values of C and M depending upon the geometry and conditions. Okay. But all the things are not being discussed over there. There are certain limitations to this. Some of the things are being discussed in that particular table at different flow conditions is being discussed. Now, here one thing as I told you that in the table it is written as Rayleigh. Here I have written as Grashof into Prandtl. Actually, this Rayleigh number is nothing but written as R A, which F is just indicating that is the film temperature properties evaluated at film temperature, and this is equal to basically GRF into PRF. So, Rayleigh number is the product of Grashof number into Prandtl number. So, nothing else except that Rayleigh number is just a product of Grashof into Prandtl number. And now, what as we have understood that the things are there are enough there are a lot of correlations available for different situations, but we will be restricting our discussions to a few and some of the situations just to have some understanding, some ideas about that. And for more detailed, more complicated situations, somebody can go to refer to some journal papers, they can go for some more textbooks who have elaborately discussed all on these particular issues. Now, one complicated expression that is that by Churchill and Chu, but before going to the Churchill and Chu expressions, I should tell that this expression is being given for isothermal. This is another point, isothermal plate or surface, sorry, not plate, it is a surface. So, it is an isothermal surface. So, that means the temperature of the wall is kept constant. So, there are two situations which may have the temperature of the wall is constant or the heat flux from the wall is constant. When the heat flux from the wall is constant, then that surface may not be isothermal. So, it is a non-isothermal surface it could be. So, then that correlation will go on changing, we will discuss that. Okay. Now, so Churchill and Chu has given some relationship which says that Nusselt average equals to 0.68 plus 0.670 Rayleigh number to the power 1 by 4 and then 1 plus 0.492 divided by Prandtl whole to the power 9 by 16 and then whole to the power 4 by 9. Okay. And this is for Rayleigh number. So, again the ranges are there important, the Rayleigh number less than 10 to the power 9, and also another expression is there that covers a wider range which says that Nusselt average Nusselt number whole to the power half, that is equal to 0.825. This is also is given by the Churchill and Chu, 8.25 plus 0.387 Rayleigh to the power 1 by 6 divided by 1 plus 0.492 by Prandtl whole to the power 9 by 16 and then whole to the power 8 by 27. So, this is for 10 to the power minus 1 less than Rayleigh number based on the length less than 10 to the power 12. So, this is the situation. So, we can find out that here it is covering this second relationship is covering a wide range of Reynolds number. I am sorry, not Reynolds number, it is the Rayleigh number. We should be very careful about that. And one thing is that the properties are evaluated at film temperature at Tf, and that we know it is Tw plus T infinity free stream or bulk temperature by 2, whatever already we have studied several times in this. Now, the question is this Churchill and Chu expressions, that these equations which are being given, it is interesting to note that this above expression, it is quite good even for inclined plate. So, when that if the angle of inclination with vertical, okay, if we say theta, if theta is less than 60 degree, then the above relation shifts of Churchill and Chu are applicable. Okay. So, this is one important thing that we can understand that even for inclined plates also we can use this. And another point we should say here that in case of say vertical tubes, another point, in case of vertical tubes, okay, the vertical tubes many a times are being taken as like a flat plate. It is assumed as a flat plate. The conditions for that is that the film thickness, or I should say the boundary layer thickness, is not large compared with the tube dia. So, therefore, what happens is that as because the tube dia is very large compared to the thickness, so the boundary layer looks to be like a flat. So, then flat plate correlations as discussed can be used. However, there is a condition is being given. A condition says to decide that whether you can use that vertical plate correlations or not, there is a condition that is being provided, and the condition says that d by L if it is greater than equal to 35 by Grashof based on length whole to the power 1 by 4. So, if diameter to length ratio, okay, so d equals to the diameter, cylinder diameter, d is equal to cylinder diameter. So, if cylinder diameter to the L ratio, if it is greater than equal to 35 by Grashof to the power, Grashof based on length, if Grashof based on length to the power 1 by 4, if that condition satisfied, then many a times we can use that vertical tube we can thought of as a vertical plate. Okay. Now, so other than that, in case of say when we consider a furnace wall, another point is the say furnace wall, the characteristic length, okay, is nothing but L is equal to area of plate divided by perimeter of the plate. It is just to remind that in Grashof number also we are using lot of is a characteristic length, and this characteristic length capital L is defined as the area of plate by perimeter of the plate. We have taken that furnace wall because many a times we have seen the rectangular furnaces are being used, and the heat losses by convection, that by natural convection takes place to the environment by the furnace wall, which are basically a vertical plate and flat plate. In that case, the characteristic length should be the area of the plate by the perimeter of the plate. Okay. Now, what we will see is that as of now, what we have discussed that vertical plate conditions, and these vertical plate conditions can also be used for inclined conditions, as well as can be used for tubes, vertical tubes, where certain conditions are there that vertical tubes can be viewed as a vertical plate. Now, second part is that if the heat transfer at constant heat flux condition. So, constant heat flux condition, we have seen previously is the isothermal conditions, that means temperature is constant. Now, is the heat flux at the wall is constant, and under that situation a modified Grashof number is used. So, modified Grashof number it is sometimes written as GRX star, GR star, modified Grashof number, it is GR star, and X means local, X means it is a function of X, it is a local. So, this is written as Grashof, normal Grashof number whatever we have seen into Nusselt X. So, and this expression is becoming just Grashof number is multiplied by Nusselt number, and Nusselt number is based on the heat flux condition. So, it is G beta QW is the heat flux which is constant, QW x to the power 4 by K thermal conductivity into nu square is the momentum diffusivity. So, we can understand that the expression of Grashof number is little bit different in this case, and therefore, it is called a modified Grashof number, and that is being used for constant heat flux condition. And then a correlationship is given for laminar range. The correlation is that nu x, which is evaluated based on film temperature condition, and that is equal to Hx by Kf. We know that it is equal to 0.60 into Grashof x star, that is nothing but the modified one, into PRF, okay, whole to the power 1 by 4, and where 2 into this is whole to the power 1 by 5, this is whole to the power 1 by 5, where 10 to the power 5 is less than Grashof x star less than 10 to the power 11, and QW is equal to constant. So, we can see here one important thing is that Grashof modified Grashof number range is 10 to the 5 to 10 to the 11, and we have told that it is in the laminar region. So, if we say it is a laminar region and the Grashof number is this, then what is the conditions for switching over from laminar to turbulent? The condition is for switching from laminar to turbulent, it is the range is being said that Grashof x star into Prandtl, this in the range of 3 into 10 to the power 12 to 4 into 10 to the power 13. So, it is relatively the range of modified Grashof number into Prandtl number is higher than 10 to the power 11, and therefore, that this is in the laminar region. Now, if we have say for turbulent region, then it becomes that Nusselt x is equal to 0.17 Grashof x star into Prandtl to the power 1 by 4, and here the range is, we can see that 10 to the power 13 less than Grashof x star Prandtl less than 10 to the power 16. So, this is the range, and we know QW is the constant wall case, wall flux case is constant wall heat flux. Now, from there we can find out the average heat transfer coefficient in this case is H bar is equal to 1 by L and 0 to L H x dx, and this is becoming 5 by 4 H x is equal to L, and we can understand that it is relatively it is little bit different from the isothermal condition cases. Okay. Now, one thing, if we try to analyze the between the isothermal case and that constant wall case and the constant heat flux cases, then we see that for constant wall temperature cases, what we have seen that Nusselt x is equal to C into Grashof, it is not modified, it is the Grashof x into Prandtl to the power m, that already we have just seen. Okay. Now, if we just multiply both the sides by say Nusselt to the power m, then we get Nusselt x to the power 1 plus m equals to C into Grashof x star. If we multiply by Nusselt x to the power m both the sides, then it is become like this, Prandtl to the power m. We will get that. Okay. So, then if I just again try to write that Nusselt x is equal to C to the power 1 by 1 plus m into Grashof x star Prandtl whole to the power m by m plus 1 or 1 plus m, whatever you say. So, that means what we are trying to say is that now this characteristics value of m for laminar case. Okay. If we say laminar case, m is equal to 1 by 4 and constant wall temperature case, and for turbulent m is equal to 1 by 3. Okay. This already you have seen for constant wall temperature case Tw, and m is equal to 1 by 4 for laminar and m is equal to 1 by 3 for turbulent, and this becomes now, if you just put it over here, then m by m plus 1 is equal to 1 by 4, and m by you can see that plus 1 by 5 and m by m plus 1, and that will be equal to 1 by 4, and this is the case for Q W is equal to constant. So, for two different cases that power is going to be changed, that is what we are seeing. For laminar case it is becoming now for constant wall condition it was 1 by 4, and now here it is becoming 1 by 5, already you have seen the equations, and for turbulent situation for constant wall condition it was 1 by 3, and here it is becoming 1 by 4. Okay. And then what we can say from here, that for laminar case H x is proportional to 1 by x cube to the power 1 by 4, okay, and then it is nearly equal to x to the power minus 1 by 4 related to that. So, and for turbulent case H x nearly is equal to constant, okay, because H x is proportional to 1 by x into x to the power 3 to the power 1 by 3. So, this is equal to say constant. Okay. So, therefore, what we can say that when turbulent free convection is encountered, so when turbulent free convection is, so this is the case for laminar case and for turbulent case, and it is for Tw equals to constant under that situation. So, for when turbulent free convection is encountered, then we can say that H x, the local heat transfer coefficient, is essentially constant with x. So, this is one very important understanding that we should have. Now, what happens is that in case of constant heat flux case, that Churchill and Chu has given a little complicated, but the correlations being given by Churchill and Chu relation for constant heat flux case, okay. And he says that Nusselt average based on length whole to the power 1 by 4, and now Nusselt average minus 0.68, and this is equal to 0.67 into Grashof L star, that means it is the modified Grashof into Prandtl whole to the power 1 by 4, and this is divided by 1 plus 0.492 by Prandtl whole to the power 9 by 16 whole to the power 4 by 9. Then Nusselt average is defined as based on the wall flux that we have already discussed, Q A by K into delta T bar. So, now delta T bar is being defined like this way. It is actually T W at L x is equal to L by 2 minus T infinity. So, it is that delta T, as we understand, delta T will go on changing as we go along the plate, and here this delta T is taken a very particular condition when the wall temperature is at the center of the plate, that means from the lengthwise it is at the middle of the plate. Okay. So, that is delta T. This way we can find out that for the vertical plates we have seen that there are certain correlations for constant heat flux condition also, and that is given by even Churchill and Chu also has given some complicated correlations, but for covering a say wide range of temperatures, wide range of conditions, flow conditions and all, which is possibly giving a better fit. Now, there are certain situations like free convection from a cylinder. If you try to see something on free convection from a cylinder. So, what we learn from there is that it can be from a horizontal cylinder, it can be from a vertical cylinder. Already we have discussed the conditions for vertical cylinder. Anyway, we will come back to this again. Say for horizontal cylinder, from or to a horizontal cylinder, and what you find that that already the same expression whatever we have seen in the table. So, table 1 can be referred, that is one case what we have discussed, the table at the beginning, and in addition to that there is a relation by again Churchill and Chu. The relation says that nu bar is equal to h bar whole to the power half. So, h bar d by k whole to the power half. So, you can understand it is the d is the outside diameter of the tube of concern that we are working on or we are interested to study, is equal to 0.60 plus 0.387 Rayleigh based on diameter of the tube, okay, to the power 1 by 6 divided by, we can have 1 plus 0.559 by Prandtl whole to the power 9 by 16. So, this looks to be little complicated, but these are the relations which are very commonly being used if somebody has to find out the values of heat transfer coefficient for such situation. And here the range is 10 to the power minus 5 less than Rayleigh based on diameter less than 10 to the power 12. This is one condition. And for laminar range, so this cover a wide range. Only for laminar range, a simpler version, simpler correlation, and that says Nusselt correlation. So, it says that Nusselt based on diameter is equal to 0.36 plus 0.518 Rayleigh based on diameter to the power 1 by 4 divided by 1 plus again the similar kind of thing 0.559 by Prandtl whole to the power 9 by 16 whole to the power 4 by 9. Okay. And this is equal to for the case 10 to the power minus 6 less than Rayleigh based on diameter less than 10 to the power 9, and we have seen that this is what is the case for free convection from or to a cylinder. Now, the question is, the second part of this is that it is a horizontal cylinder. The first part was from a horizontal or from or to a horizontal cylinder. Now, the second part is B, it is that vertical cylinder case, and we have already discussed a vertical cylinder can be considered as a flat plate when d by L is greater than or equal to 35 as gas up to the power 1 by 4, that already we have discussed. And in addition to that, when the diameter or is small, so it is the first case is that can be considered as flat plate when we have already discussed d by L greater than or equal to 35 by gas of L whole to the power 1 by 4. This is one case, and when the diameter is, this is the second case, is when the diameter is small and the condition is not fulfilled, then these are very rare cases, and in that situations we have to use some other correlations can be used. And for that there are some literature references which can be considered for a typical literature. Is by McCoys and Sparrow. WJ and Sparrow EM, and they have already a work on published in a Journal of Heat Transfer. It's volume 96, 1974, and page number 178. So, this reference a typical literature which can be considered when the vertical cylinder diameter is small and it is not falling or it cannot be considered or simplified as a vertical plate under the situations. Now, in addition to this, now if I consider a case of say horizontal surface with constant heat flux. So, there are many situations which can come up for free convection situation. So, horizontal surface with constant heat flux. Okay. So, under that situation there are something is being given that Nusselt average is equal to 0.13 Grashof based on length into Prandtl to the power 1/3, and here Grashof based on length into Prandtl is less than 2 into 10 to the power 8, and this is equal to 0.16 into Grashof L into Prandtl to the power 1/3, and here 2 into 10 to the power 8 less than Grashof based on length into Prandtl divide, and basically these are nothing but a Rayleigh number based on length into 10 to the power 11, and in both the cases that heated surface facing upward. So, hot surface facing upward. Okay. And then there is another one that Nusselt based on in that particular case length, average Nusselt number is equal to 0.58 into Grashof L into Prandtl to the power 1/5, and this case 10 to the power 6 less than Grashof based on L into Prandtl into less than 10 to the power 11. So, here the hot surface is facing downward, hot surface facing facing downward. Fine. And then all properties in this particular case, all properties except beta are evaluated at Te, and that is equal to Tw minus 0.25 into Tw minus T infinity. T infinity is the free stream temperature or the stagnant film temperature. Okay. That is what is being done. Now, in addition to that, there is a relationship for free convection from sphere. So, we have seen that cylinder case, we have seen the flat surface case. Now, we would like to see the cylinder case, convection from sphere. Okay. Now, and in this situation, what we know that Churchill has suggested the relationship that Nusselt is equal to h bar d by k, and this is equal to 2 plus 0.589 Rayleigh based on diameter to the power 1/4 by 1 plus 0.469 by Prandtl whole to the power 9/16 whole to the power 4 by 9, and here Prandtl is less than 0.7, Prandtl is greater than equal to 0.7, and Reynolds Rayleigh based on diameter is less than equal to 10 to the power 11. So, this is the another free convection situations from sphere. Now comes that free convection situation can also arise in an enclosure. So, we can have different type of, so if we try to see that case, that free convection in an enclosure. So, we have already seen that this enclosure can be, we can have say horizontal, inclined, vertical, rectangular enclosures in space between concentric. So, we can have say rectangular enclosure, we can have cylindrical enclosures, we can have spherical enclosures. So, depending upon the geometry and the kind of enclosure, and the enclosure can also have of different kinds, like in case of say rectangular enclosure, then you can have the inclined surfaces, some surfaces are inclined, some surfaces are vertical, there will be some horizontal surfaces also. So, that way we can have a wide variations in the geometries are possible, and for that one can refer to a literature by Churchill, S.W., and it is based on free convection in layers and enclosures. So, we can understand, so there are many things, different types of enclosures which is not possible to be covered up in this particular lectures or in this particular heat transfer course. Somebody, and these are mainly related to higher studies, more in-depth studies, in the very specific studies, and focus studies in the areas of free convection. So, those who will be interested, they can refer to this literature to find out how the correlations are and how to make use of those correlations for finding out the values of heat transfer coefficients. So, layers and enclosures, it is in heat exchanger design handbook is basically it is a heat exchanger design handbook, and it is by Hemisphere Publication Company, New York, 1983. However, we can still suggest some relationships, typically some relations. If we try to see that, is a typical one is by one relation is like this, that Nusselt average based on wall temperature, it is equal to 0.42 Rayleigh based on wall temperature condition to the width based on width, and Prandtl to the power 0.12, I am sorry, is given as 0.012 L by W to the power minus 0.3. So, this relationship is based on the width, it is not Nusselt based on the width and Rayleigh based on the width. Okay. So, for 10 less than L by W, W is width, L is the length, less than 40, and 1 less than Prandtl less than 2 into 10 to the power 4, and 10 to the power 4 less than Rayleigh based on width less than 10 to the power 7. So, this is a condition. For this condition, there is some relationship is available to calculate the values of Nusselt number. Similarly, we have another relation like Nu average based on width is equal to 0.046 into Rayleigh based on W width to the power 1/3, and in this case 1 less than L by W less than 40 again, and 1 less than Prandtl less than 20. You can understand that Prandtl number is less now in this case, and 10 to the power 6 less than RAW less than 10 to the power 9. So, this is for a wider range of for a higher range of Rayleigh numbers. This relationship is used. So, these relationships whatever we have discussed, these are free convection heat transfer in a vertical rectangular cavity. So, the above relations are for vertical rectangular cavity or enclosure, whatever you can say. And then there is another relationship between two concentric horizontal cylinders. So, this is also an enclosure between two concentric horizontal cylinders. So, this is also an enclosure. So, in this case there is an effective thermal conductivity is defined. So, K effective by K is given as 0.386 into Prandtl by 0.861 plus Prandtl whole to the power 0.25 into Rayleigh C effective whole to the power 0.25, and here 10 to the power 2 less than Rayleigh star C less than 10 to the power 7. So, this is for concentric cylinders case, that is why it is a Rayleigh star CE, and now Rayleigh star CE is defined as is a modified Rayleigh number, and it is defined as some complicated relations ln dO by di whole to the power 4 divided by L cube into di to the power minus 0.6 plus dO to the power minus 0.6 whole to the power 5, okay, and then Rayleigh based on the length. So, in this case di is OD outside diameter dia of inner tube, DO inner inside dia of outer tube, okay. Then L is equal to DO minus DI, and that is equal to characteristic length in the annulus, okay, and K effective is the effective thermal conductivity and this rate of heat transfer by natural convection per unit width per unit length is the same at that as that through the annular region having an effective thermal conductivity KEF. Okay. So, Q equals to twice pi KEF effective into Ti minus To by ln dO by di, and Ti and To are temperatures of inner and outer cylinder walls. Okay. So, now what we are going to discuss is another situation which we always come across, that is called combined free and forced convection. So, this is a particular situation that many a times we come across, combined free and forced convection heat transfer. And what happens in case of combined free and forced convection heat transfer? When there is a fluid flow also that takes place, along with the fluid flow takes place and then heat transfer takes place, then there is a possibility that both convective heat transfer as well as the natural free convection heat transfer and natural convection heat transfer can take place together. So, when there is no flow of the fluid, there is only natural convection. When there is a flow of fluid, then always there will be some amount of natural convection coupled with the forced convection heat transfer. Now, we have to decide that whether free convection heat transfer will be an important free convection heat transfer will be an important phenomena when all the time when there is a flow. Actually, it is being found that most of the situations when the flow is very large, that time the free convection situation becomes almost it's not having much of use, but it's not dominant or negligible, we can say. Whereas, when the flow is laminar, when the flow is small, and then we can have a good amount of contribution for natural convection with respect to the forced convection case. And therefore, there is a condition that is being given that when and Grashof L by Reynolds L square. So, Grashof number is the Grashof number says that it is the forced convection it is the flow behavior in case of free convection situation, and Reynolds number is the flow behavior in case of forced convection situation. So, these two terms are taken into consideration. If they are very less, then it is called negligible, less than 1, then we can call negligible free convection. Okay. And when Grashof L by Reynolds square is greater than much greater than 1, then we can say the negligible forced convection, because we can understand that Reynolds number is becoming for this case effect of Grashof number is much more compared to the Reynolds number case. And if Grashof L by Reynolds square is nearly equal to 1, then we can say that mixed convection is important. Okay. Now, there is a correlation that is being given by Brown and Gaussian. They have given a correlation for laminar flow, okay, and horizontal tubes through. So, under that situation, that Nusselt equal to 1.75 mu b by mu w to the power 0.14 into Zz, this whole greatest number, plus 0.012 into Zz into Gr whole to the power 1/3 whole Gr to the power 1/3 whole to the power 4/3 and then whole to the power 1/3 again. So, this where Zz is greatest number and mu b is evaluated at bulk temperature. This is mu b by mu w. Mu w is evaluated at wall temperature and others properties are evaluated at film temperature Tf. Now, there is a situation that equations that when there is a flow through a tube, say a vertical tube, fluid is so flow through flow is upward, and another case A, case B is flow is downward, and point is that say natural free convection is considerable amount. Then what happens? So, what we can see that in case of then what happens to the flow situations in these cases. So, for first case what we can see that the flow is upward and say it is a hot surface, upward and hot tube surface, and it is also hot tube surface. So, what we can understand in the very first case, the fluid will be flowing upward, and because of natural convection also the flow will be upward. So, the natural convection flow will be adding with the flow of the fluid. So, this is called aiding flow, and in the second case, the case B, fluid will try to go upward, but natural convection fluid will try to go downward, and natural convection will try to make the fluid to go upward. So, there will be an opposing flow situation. So, this kind of flow situations can be encountered when we have flow through vertical tubes and all. So, under that situation, so when there is a mixed flow, we can have the Nusselt number mixed for the mixture is equal to Nusselt number free to the power m plus minus Nusselt number forced to the power m, and m is nearly equal to 3. So, when we have such cases, so we try to find out the Nusselt number for free convection situation, we will try to find out the Nusselt number for forced convection situation, and then we will try to find out that for the mixed situation, and that is equal to the m is equal to 3 for these cases. So, plus and minus is for aiding flow and when there is a opposing flow situation. Okay. So, this is all about this particular free convection heat transport, whatever we had to discuss, and maybe I will be putting some exercise problems, I will with some hints I will putting afterwards, and then one can go through those problems, how to apply these concepts or equations for solving certain heat transfer problems related to natural convection and combined free and forced convection situation. Now, in the next class onwards, next lecture onwards, we will discuss on some other module, particularly we will be trying to take up that boiling and condensation heat transfer. Thank you very much.